Good morning, everybody. Nice to see that so many people are interested in what we're doing. I will try to give an overview of our project. First, maybe let me recall the title. CoSSMic is actually an acronym standing for Collaborating Smart Solar-Powered Microgrids. My talk, I will first give you some facts about the project, like budgets and such. Then I will introduce the problem that we addresses, and then talk about the CoSSMic solution. And finally, a little bit about prototyping and evaluation of our solution, and conclude by mentioning some challenges that we have met and the remedies that we see for that. Okay. It's FP7 and European Union funded project under the 7th Framework Program. It started in October 2013 with a duration of 39 months and a total budget of 4.2 million euros. We are funded under the so-called public-private partnership on energy efficient buildings. And we have a website where you can see more details about the project if you're interested. The consortium, as already mentioned, SINTEF is the coordinator. We have ISC and Sunny Solar Technique and the city of Constance, here in Constance. We have the second University of Naples and the Provincia di Caserta, which is also close to Naples. Then we have the Norwegian University of Science and Technology, and finally, and the University of Oslo. And finally, our dissemination partner taking care of recording this event, Bokia.com. Let me start by clarifying what we mean by this term solar-powered microgrids. Basically, it's a building with solar panels on the roof or on the facade, if you prefer, and a number of power-consuming devices like refrigerators, washing machines, dishwashers, heat pumps, and also charging electric vehicles. And some of them also have a stationary battery. And maybe unlike some microgrids that you may have read about, we are assuming that there is also a connection to the public grid. This is not an isolated, we're not talking about isolated microgrids, but building microgrids connected to the public grid. The problem we are addressing is, I guess in this audience, well known, that the solar panels they do not always produce energy when we need it. Sometimes they produce much more than we need, and sometimes they do not produce at all. For instance, we have sorry for that. We have here a recording from a number of houses in Constance that we have instrumented, showing, I don't know how typical this morning is, but you see the yellow curve is the consumption, while the white one is the production from the solar panels. This is from a group of houses. And as you see, there are consumption here that cannot be satisfied by the solar panels. And we have here a period where the production, where the consumption is much lower than the production from the solar panels. So the idea is that if we can shift some of these loads from periods when there is no production to a period where there is surplus production, then we can exploit much better the capacity of the solar panels. However, to do that, you have to be there to kind of switch on your things exactly when the sun is shining, and that for most people that is not very convenient. So our approach then is to introduce smartness or automation to automate the control of energy consuming tasks in the house. Of course, the inhabitants have to set their rules. For instance, if you want to run your washing machine, you can turn it on in the morning, but you can tell the system that it need not be finished until I'm home in the evening. So then the system has the freedom to run the washing machine when there is available power from the solar panels. And in addition, we introduce collaboration between a number of buildings in a neighborhood, so that we can exploit the variation in consumption patterns between different houses to even increase further the self-consumption from the solar panels. So then a little bit about how it works. We place a small controller in each house. In our prototype implementation, this is a Raspberry Pi, a small microcomputer. This is connected to the consuming devices, or rather to smart plugs between the consuming device and the controller, so that the controller can switch the power on and off on the various devices. And they communicate by various wireless protocols with the controller. And then this controller communicates with each other through the local Wi-Fi and the internet. So they talk with similar controllers in the other houses in the neighborhood. And it also communicates with supporting services in the internet, like weather forecasts and pricing signals from the grid, so that the controller can predict both the production from the solar panels based on the weather forecast, and it can predict the prices of the power from the grid and schedule the running of these devices in an optimal way. Yes, and we call this then an energy smart neighborhood. Some more features of the system. In order to motivate the users to actually use it, we have experimented with using ideas from the gaming field to provide encouraging feedback to the users, like providing ranking among neighbors, how much they contribute to this common community. It's a decentralized system. The controllers communicate peer-to-peer with each other, and it doesn't require any central authority to control this system. So a group of neighbors can agree to install this system, and the controllers will find each other and establish the neighborhood. It has also been a goal for us to produce a low threshold technology that can easily be adopted by anybody. Low cost, we're using low cost hardware like the Raspberry Pi, and also these smart plugs are fairly cheap and fairly easy to get nowadays. We try to make it easy to install and use. We only use existing communication infrastructure like the Wi-Fi that is already in your house and the internet. And there is a lot of learning inside, so you do not have to describe the devices to the system. The system automatically learns what is the consumption profile of the various devices, like the washing machine or the dishwasher or the water heater. After some time, it will learn that when they turn on, they need this much energy. And they can use that in the planning. Okay, so what are the benefits here? I guess I mentioned it mostly already, but just to summarize, this will lead to increased self-consumption, which means less or smaller power bills from the power retailer, and in turn increased return on investment on your solar panels. It will also lead to reduced peak demand on the grid, as Christian mentioned in the introduction. These variable and not so predictable renewable energy sources causes certain problems for the existing public grid. So we think that we can make it or alleviate that by reducing peak consumption or consumption peaks, and also reducing feed-in peaks on the public grid. And finally, demand response is a much talked about issue in the smart grid. Generally, individual household has been considered much too small to actually participate in such schemes. But a neighborhood of maybe from 50 to 100 houses could be big enough to actually participate in such schemes, and our system could realize that. It is not, our prototype cannot do that, but the concept could easily be evolved to also include that. And finally, all this with less storage capacity. As you may know, the storage is perhaps the most expensive component in solar system, and by coordinating the use of the total storage resources in the neighborhood, we can reduce the amount of storage needed to achieve a certain increase in self-consumption. So our research approach has been to build a prototype of this system using a user-centric design approach. We have involved potential users, both here in Constance and in the province of Caserta, during the design. And then we have installed the system in 2 trial sites. There's one in Constance with 12 buildings, a mix of private houses and small industries. There are schools, and there's another trial site in Caserta with 5 buildings. Unfortunately, there are some problems with legislation and regulation that does not always allow us to experiment with the full potential of the system, like restrictions on feed-in and restrictions on the use of storage, and also tariffs. The current tariffs provided by the power retailers are not always favorable for this kind of system. To compensate for that, we have also developed a simulation environment where we can model the neighborhoods and run simulation where our system, the same code that is running in the controller, can run in a simulated environment where we can experiment with the aspects that we cannot do in real life. For example, to scale up to much bigger neighborhoods, to experiment with alternative dimensioning and mounting of solar panels and batteries, alternative pricing models, and also to do things that are not allowed in the current electrical system. Okay, then I mentioned some challenges that we have met. I think I probably mentioned some of it already. The shortcoming of the tariffs, for instance, the peak shaving is not really rewarded in current tariffs, although power-based tariffs rather than energy-based tariffs are becoming more and more in demand, I think. So, and that, of course, will be a a big advantage for our system that can shape peaks. Then, of course, there is this, when you have this neighborhood, some neighbors maybe contribute more than others to the common reduction in consumption from the grid. But in the current system, each neighbor will have their own agreement with the retailer, and there will not be any balancing of the power grid according to how much they have contributed to achieving these benefits. So what we need to do is to work with the DSOs and the retailers to come up with tariffs that better acknowledges this kind of neighborhoods in order to, if we should succeed to have a wider deployment of this kind of neighborhoods. Then we have a problem with user acceptance. As I mentioned, the user have to set their constraints. When do the washing machine need to be finished? How much do I allow the heat pump to be, or how much do I allow the temperature of my house to fall? So I can have some flexibility with the heat pump and such. And users are generally reluctant to put in the extra effort to learn how to do it and to actually set these constraints that are needed to give the system some flexibility. Although we try to involve the user in the design, I think maybe we do not have a final solution for this. I think the answer is higher degree of automation, and for that we need better control interfaces to the devices, so we can know more about the devices and control them in a more sophisticated way. Then we have the problems with prediction, that the weather forecasts are not sufficiently accurate that we can very precisely predict the output from the solar panels. And hopefully in the future also weather forecasts will improve and become more accurate and have more frequent updates, so we can have better predictions. Yes, and the control interfaces I already mentioned. So that concludes my talk.
Okay, thank you very much.